take a look at Mars. Today, it is a frozen, rusted, silent wasteland, a desert where temperatures regularly drop to minus 150 degrees Fahrenheit, and the soil is caked in toxic chemical salts, but beneath this dead red mask lies a ghost. 4 billion years ago, Mars was a thriving blue planet. It had rivers wider than the Amazon, deep oceans covering its northern hemisphere, a protective magnetic shield, and a thick insulating atmosphere. It was Earth's true sister world, a place where life could have, and perhaps should have, begun. So how did a paradise become a planetary grave? For decades, we've been told a very simple, tidy story. Mars was born too small. Its core cooled down naturally, and the solar wind slowly stripped away its life-giving atmosphere over billions of years. It's a tragic yet quiet geological death. But what if that story is incomplete? What if the red planet's death was far more violent, far more sudden, and shockingly radioactive? When scientists began analyzing the very dust and atmosphere of Mars, they didn't just find dirt and carbon dioxide. They found chemical signatures that shouldn't exist on a naturally dying world. Signatures that on Earth are only found in the wake of thermonuclear catastrophes. Our story begins in 1976, when NASA's Viking landers first touched down on the Martian surface. Their mission was to search for signs of life, but while the biological experiments returned highly controversial and ambiguous results, the chemical readouts of the atmosphere sent shockwaves through the scientific community. Now, xenon is a noble gas. It's heavy, it's highly stable, and it doesn't easily react with other elements. Because it's so heavy, it should actually be harder for Mars's weak gravity to retain compared to lighter gases. Yet, the sheer abundance of 129 xenon in the Martian atmosphere is a massive glaring outlier in our solar system. It is vastly higher than what we find on Earth, on Venus, or even in the solar wind itself. So, what produces high concentrations of 129 xenon on Earth? We see this specific isotopic spike in very limited scenarios. The most prominent fast neutron nuclear fission. When a thermonuclear weapon detonates, or when enriched uranium is processed in a reactor, it releases a flood of high-energy, fast neutrons. These neutrons smash into uranium or plutonium atoms, initiating a violent fission chain reaction. A major byproduct of this high-energy violence is the radioactive decay of iodine-129, which has a half-life of 15.7 million years, ultimately decaying into stable xenon-129. In fact, if you analyze the Earth's atmosphere today, you can find a distinct, unmistakable spike in 129 xenon left behind by humanity's atmospheric nuclear weapons testing since 1945. And on Mars, that signature is exponentially stronger. It's as if Mars is wearing the chemical radioactive fingerprint of a massive, planet-wide nuclear event. But how could a planet with no industrial civilization end up covered in nuclear ash? This anomalous data led Dr. John Brandenburg, a highly respected plasma physicist who worked on space defense technologies and the Clementine mission to the Moon, to propose a hypothesis so controversial. It sounded like pure science fiction. Brandenburg argued that the high levels of 129 xenon, combined with elevated levels of radioactive potassium-40, uranium, and thorium on the Martian surface, could not be explained by slow natural geological processes. He mapped out the concentration of these radioactive isotopes across the Martian surface using data from NASA's Mars Odyssey orbiter. What he found was startling. The radioactivity wasn't distributed evenly. It was concentrated heavily in two specific massive regions, Mare Acidalium and Utopia Planum. According to Brandenburg's calculations, these hotspots represent the epicenters of two colossal mid-air thermonuclear explosions, blasts equivalent to billions of megatons of TNT. He argued that these weren't underground deposits but massive airbursts that blanketed the entire planet in radioactive debris. The heat from these blasts would have been so intense that it would have instantly vaporized the oceans, stripped the atmosphere, and melted the surface soil into a glassified silica-rich substance similar to trinitite, the radioactive glass created in the New Mexico desert during the world's first atomic bomb test. Brandenburg went even further, suggesting that the existence of these specific isotopes point to a deliberate artificial intervention, a prehistoric nuclear war that wiped out a young Martian biosphere. It's an idea that captures the imagination, offering a terrifying answer to the Fermi paradox. Perhaps the universe is silent because civilizations inevitably destroy themselves or are destroyed by cosmic anomalies. But mainstream science was deeply skeptical, and for good reason, because while the isotope data is real, the universe has a way of creating terrifying phenomena all on its own, without the need for science fiction warfare. To answer that, we have to look at our own planet. In 1972, French scientists analyzing uranium ore from a mine in Oklo, Gabon made a baffling discovery. The uranium ore was depleted of uranium-235 in a way that only happens inside active nuclear reactors. After years of study, geologists realized that 1.7 billion years ago, Oklo was a natural nuclear fission reactor. Deep underground, a concentrated deposit of uranium became saturated with groundwater. The water acted as a natural moderator, slowing down neutrons and allowing a self-sustaining nuclear chain reaction to begin. This natural reactor operated off and on for hundreds of thousands of years, generating heat and nuclear waste products before finally burning out. If Earth could host natural nuclear reactors, could Mars have done the same? But on a catastrophic scale. Many planetary scientists argued that early Mars was highly rich in heavy radioactive elements like thorium and uranium. Because Mars has no plate tectonics to constantly recycle and churn its crust like Earth does, these heavy dense radioactive elements could have concentrated in massive, localized underground deposits. Over millions of years, as water seeped down into these concentrated radioactive veins, it could have triggered massive natural, underground nuclear reactions. If these natural reactors became unstable, they could have suffered catastrophic steam explosions, breaching the surface and scattering radioactive isotopes like xenon-129 and potassium-40 across the northern plains. But even a natural nuclear explosion is only a small part of the story. The true definitive killer of Mars didn't come from a sudden blast. It was a slow, agonizing, and completely natural cosmic execution.